Welcome to day 4. We're going to be looking at arc length and surface area parametric equations today, and we'll go through each of the homework problems. So for your dy over dx, take your dy over dt, which was 3, over your dx over dt, which was 2. Then your second derivative is the derivative of 3 halves, which is 0, over your dx over dt, which was 2, so your second derivative is 0. At t equals 3, the slope is 3 halves, because it was always 3 halves, and there's no concavity, since it was 0 always for the second derivative. For 7, you get 2t plus 3 for dy over dt and 1 for dx over dt. So then your second derivative, the derivative of the dy over dx is, or the derivative of the 2t plus 3 is 2 over the dx over dt, which was 1, so you get 2. Concave up because the second derivative is always positive. Didn't even have to consider the time. Put in your negative 1 for t, and you get your slope is 1. Next one, you got your dy over dx by doing your dy over dt over your dx over dt. Divide out the 1/2, swing those to the opposite spots in the fraction, and you get your dy over dx. So at t equals 2, that's going to give us square root of 2 over 1, or in other words, square root of 2 for the slope. Now for your second derivative, you have to do the quotient rule. Now I chose to neaten it up. You could just sub your 2 in right there after you do the quotient rule, and you would get a negative, so it's concave down. But just to show you the neatening up, so those negative exponents swing to their denominators, and then that's really 1 over 2 square root of t in the bottom, so multiplied by its reciprocal. When you multiply the 2 square root of t through, this 2 square root of t ends up wiping out. The 2's wipe out here, and you just get a t on top. You can get a common denominator by multiplying top and bottom by square root of t minus 1, so that gives us this. Combining your like terms gives us that, and multiply by the reciprocal gives us negative 1 over the t minus 1 to the 3 halves. Well, subbing in the 2 for t would give us a negative, so that's why it would be concave down. Again, you didn't necessarily have to neaten that up. Could have just subbed in the 2 here and neatened it up with numbers to find that it's negative. In 13, make sure you did your chain rule for each of those. One set of coses, one set of sines divides out. You're left, and the 3's divide out, so you're left with negative sine over cos, so negative tangent. At pi over 4, tangent is 1, so we get negative 1 for the slope. Our second derivative, the derivative of the negative tan theta, would be negative secant squared, and then over the dx over dt. So cos squared on the bottom, if you move that up, it's a secant to the 4th, and then you get the sine could come up as a cosecant if you wanted, or you could keep them where they are. It may have even been easier to bring the secant squared down as a cos on the bottom. That might have been easier. All of, at pi over 4, all of them are just 1s, so we have negative over a negative, which will give us a positive, so concave up. I should take that back. They're not all 1s. They're all the same. They're all 1 over square root of 2 or square root of 2 over 2. But because they would be positive for all of them and all we care about is the sign, they would all end up as positives for our secants, cosines, and sines. So we just worry about the negative divided by the negative. All right, 15 was really hard. So start out, do your dy over dt over dx over dt. You can neaten that up to be negative 2 sine cubed times cos theta. So a tricky thing was finding what value of theta do we have for that point. So in that first one, that's the blue that I have there. So I took the minus 2 over radical 3, set it equal to 2 cotangent theta. Divide by 2, you get negative 1 over radical 3. Do the same thing for the sine with the y, and you get plus and minus radical 3 over 2. Well, cotangent's negative, so it's got to be in either quadrants 2 or 4. And sine, we had both options. So there's your 2 triangles for your 2 options. Well, notice sine and cos are both 2 odd powers. So in the green triangle there, sine will be positive, cos will be negative, and in the blue, cos will be negative, sine will be positive. So no matter which option you do for your triangles, you're going to get the same slope. So I just chose to do it at theta equals 2 pi over 3, which was the green one. You'll get the same slope answer either way. Just I have plus and then minus. You would have had minus and plus if you decided to do the blue triangle. So that should have given us a slope of 3 radical 3 over 8. So then we do y minus our y value of 3 halves equals our slope times x minus our x value, which ends up as a plus 2 over radical 3. For 0, 2, that's what I got in the green here. Set that 0 equal to the 2 cos tangent theta. You end up with cotangent is 0. So that means the cos has to be 0. For the sine, or for the 2, set it equal to 2 sine squared. So sine will eventually be plus or minus 1. So we either have to have pi over 2 or 3 pi over 2 to have cos be 0 and have sine be plus or minus 1. Well, because we've got a cos at the end there and it's going to be 0, either of those options, it doesn't matter. So I just hypothetically chose the pi over 2 there. If you had chosen the 3 pi over 2, you just would have had the negative 1 in parentheses. Again, it's not going to change your slope. So y minus 2 equals 0 times x minus 0, which simplifies to y equals 2. And then the last one, same idea. Set 2 radical 3 equal to 2 cotangent theta. Divide the 2 over, so cotangent's a positive radical 3. Sine will eventually be plus or minus 1 half. So you are in either the first or the third quadrants based on your signs of your trig functions. And sine and cos are either going to be both be positive or both be negative. So, and again, we had odd powers there, so the slope, it won't matter which option you picked. You just had to pick one of the two, and then just put it in your point slope form of a line there. Y minus a half equals negative radical 3 over 8 times x minus 2 radical 3. So that was a really hard question. Going on to 17 and 19. So take your derivative of the dx over dt, you get 2. dy over dt, you get 4. Divide them, you get 2. If you set, or if you put t in for each of them, you get the 0.4 comma 3, and then just write your point slope equation of the line. Pretty similar idea for the next one, just your dy over dt and dx over dt weren't constants, you had to sub in the negative 1. For 21, we end up crossing twice. We're crossing at 0, 0. So that would be based on our originals, because the y has to be 0. So that would be when sine is 0, pi, 2 pi, and so on. Well, once you get, it takes pi for it to go around once. So the 2 pi and 3 pi are repeats. So we're only going to do it at t equals 0 and t equals pi. Do your dy over dt over your dx over dt. Sub in 0 for t, we got a slope of 3/4. So we had the y minus 0 equals 3/4 times x minus 0, which is just y equals 3/4 x. Do the similar thing for pi. Only difference is you get the slope of negative 3/4. (28) Do your dy over dt over dx over dt. Horizontal when the numerator is 0, so set that equal to 0. You get t is plus and minus 1. So when t is equal to 1, sub it into the original x and y, and you get the 0.2, negative 2. When t is negative 1, sub it into the original x and y, you get 4, 2. It's vertical when the slope is undefined, so that's when our dx over dt is 0. Set that equal to 0, you get t is a half. Fill those in the original, you get 7/4 and negative 11/8. For 33, our dy over dt over our dx over dt, if you neaten it up, you eventually get 1 over sine theta. So therefore, the numerator will never be 0, so it's never a horizontal tangent. And for your denominator, that'll be 0 at all your integer multiples of pi. So you could say theta equals n pi, and when you sub that back in, depending what multiple of pi that is, you will either get 1, 0 or negative 1, 0. So today's first topic is arc length of a planar curve. So the idea behind arc length is that we saw in a previous unit is we did Pythagorean theorems of little lengths. Then whatever that hypotenuse value was, we added them all up with an integral, and that eventually gave us the length of the whole thing. So we're going to do a similar idea here. So say we have change in x squared plus change in y squared equals change in s squared. Get the change in s squared by itself. Well, we want our functions in terms of t's, so we're going to force that. So let's multiply each of those by delta t squared over delta t squared. We'll slide one of them under the delta x and the delta y squared and pull out the delta t squared. Square root of delta t squared will just be delta t, and then we could put those in one parenthesis. So really what it'll eventually give us is the integral of just our x component derivative squared plus our y component derivative squared, all under a square root. And you've got that written nicely down on the bottom. Now, under the box there is an important thing to remember. This is only true if the curve is smooth. So if you have any like corner points or abrupt changes, it would not be true over that interval. And we have to make sure it doesn't intersect itself. If it does either of those things, we just might have to do multiple integrals for each of the smooth parts. So we're going to see if we can find the length of this from 0 to pi. We might recognize that from before, but that is will end up being a circle, so it's smooth everywhere. So we're doing the integral from 0 to pi of the square root. And let's just list what our dx over dt are and dy over dt are. Dx over dt will be minus 4 sine t. And dx over dt will be, dy over dt will be positive 4 cos t. So we've got to do our dx over dt squared, so minus 4 sine t squared, plus dy over dt, so 4 cos t squared, and then dt on the end. So we have 4's that are going to get squared there. So this is the integral from 0 to 4 of square root of 16 sine squared t plus 16 cos squared t dt. And I don't know why I wrote that as 0 to 4. These should be 0s to pi's. So we can rewrite this and pull the square root of 16 out. Well, square root of 16 is just 4. And sine squared plus cos squared is just 1. Square root of 1 is 1, so this is just 4 dt. The antiderivative of 4 is just 4t. We're going to evaluate it from 0 to 4. So we'll have 16 minus 0. I don't know why I just wrote the 4 again. Sorry, that should be 0 to pi. So we'll have 4 pi minus 0 equals 4 pi. Now, if we think about this, remember I mentioned at the beginning that this is a circle. 0 to pi would be half of the circle. The circumference of a circle with radius 4 would be 8 pi. That would be all the way around. So 0 to pi should be half that. And notice we got 4 pi. All right, a circle with radius 1 rolls around the outer edge of a larger circle with radius 4. Point A is on the smaller circle, and we are having the locus of points determined by our path is represented by these functions. So first thing I want to show you is just a little video of that. Now the video I found has it so the radius is 3 and 1. So it's going to look slightly different. So there's the smaller circle rolling around. So notice there was 3 sections because the bigger circle had a radius of 3. So the difference for ours is we're going to have a radius of 4 for the large circle. So when we do that, we'll end up with a picture like this. So the main thing to note in this is that it is not smooth all the way around. When we go around a full 2 pi, there are 4 separate sections, so each of those sections is going to be pi over 2. So the strategy for this, because they're each the same, is we're just going to do the integral from 0 to pi over 2 and then multiply it by 4. So with this, it's a good idea to just graph it first to make sure that it is going to be smooth. So notice here for arc length, we've got 4 times the integral from 0 to pi over 2. Our dx over dt would be negative 5 sine t plus 5 sine 5t by the chain rule. And maybe I'll write over here our dy over dt is going to be 5 cos t minus 5 cos of 5t. So from there, we'll just have our square root. It's going to be kind of big. We'll have our dx over dt part squared plus our dy over dt part squared, and then dt. So we are going to have negative 5 sine t plus 5 sine of 5t. Then we'll have 5 cos t minus 5 cos of 5t. All right, so what I'd like you to do is pause the video and punch this in your calculator. Make sure you are in radian mode as you're doing it, and be really careful of like parentheses and things like that. Lots of spots you can go wrong. So pause the video, and when you hit play, a thing will pop up for you to put in your answer. All right, and you should have found that this worked out nicely as 40. So that's how you do arc length of a um, planar curve or a parametric. Could say either. So the other thing we're going to look at is surface area. So from unit 5, we looked at surface area, and it was just 2 pi times the radius times the arc length. So for us, our options are going to be, we could have 2 pi. If we're going over the x-axis, our radius will just be, oh, I guess I should throw the integral in there. 2 pi from a to b. We'll have the radius would be our y of t, and then it will just be our arc length. So we'll have dx over dt squared plus dy over dt squared, and then dt on the end. Now, if you were going over the y-axis, the only thing that's changing is your radius. Our radius would be going that way, so that's an x. So we would have x of t as our radius. And then this would just all be the same. So surface area parallels pretty well with what we did earlier. So we'll finish off the video with 2 surface area examples. So our dx over dt would be negative 3 sine t. And our dy over dt would be 3 cos t. So for our surface area, we're going to have 2 pi. They told us our interval is 0 to pi over 3. Now the big decision we have is our radius. We're going over the x-axis, so that would be our radius, which is a y. So we're going to have our y of t. So our y of t was 3 sine of t. And then we'll just do our square root. We'll do our dx of t squared plus our dy of t squared times dt. Now, sometimes these ones will be ones where you just sub in. We're going to try and do this one algebraically. And you'll see on the homework, it'll say to try all but number 35 algebraically. So for this part here, we're going to end up with a 9 sine squared t plus 9 cos squared t. Well, we kind of saw that in the last one. If you pull the 9 out, square root of 9 is 3, you'll have sine squared plus cos squared, which is just 1. So we're going to have a 3. This is just going to become 3. So the 3, and the 2 are going to give us 18 pi out front. We'll have 0 to pi over 3, and all we'll have left is sine t dt. So if you're being asked to do it algebraically, then it should be a way to neaten up and not be too bad. And again, on the homework, just watch out. Some of the directions might say you can do it on your calculator, but I would like you to do them all algebraically except for 35 on the homework. So antiderivative of sine, we just got negative cos. So we got 18 pi negative cos of t. And we're going from 0 to pi over 3. So that's 18 pi minus cos pi over 3 plus cos of 0. Pi over 3 is 60. So we're just going to have 18 pi minus a half. And then plus 1. So that'll be a positive half times 18 pi. So in other words, gives us 9 pi for the surface area. Now the bottom one, we're going to do the same equations just over the y-axis. So the only difference that'll change is our radius now is an x. So we're going to have the 2 pi out front. We're still going from 0 to pi over 3. But now we're going to have our x component, the 3 cos t is our radius. And we'll still have the same thing in here. We'll have from above that was negative 3 sine t squared plus 3 cos t squared and then dt. Well, remember, this ended up all just being 3 because it was square root of 9 times a square root of sine squared plus cos squared. So we're going to again have 18 pi from 0 to pi over 3. And this time we'll just have cos t dt. Antiderivative, we'll just have sine t from 0 to pi over 3. So this is 18 pi times our sine of pi over 3 from our triangle a second ago. Sine would be square root of 3 over 2. Minus sine of 0, which is 0. So if we multiply the 18 pi, we'll just get 9 radical 3 pi. That's it for this video. Again, remember on the homework, do all but 35 algebraically. Have a great rest of your day.